So good afternoon, ladies and gentlemen, and welcome back. So at this point, we look at IS-IS principles and configuration. IS-IS, like OSPF, is an IGP. Again, like OSPF, it uses SPF to calculate its routes. And it's also a link state. It's also a link state routing protocol. Okay. So IS-IS stands for intermediate system to intermediate system. The system you're talking here is just the router, so like router to router. So IS-IS, intermediate system to intermediate system. So it's a link state based interior gateway protocol, uses SPF algorithm to calculate routes. IS-IS is a dynamic routing protocol, meaning that the routes are learned automatically. It was initially designed by the International Organization for Standardization, ISO, for what we call CLNP, to support what we call connectionless network protocol. Now, in order to support routing, IS-IS was tweaked by the Internet Engineering Task Force, and it was extended and modified in Request for Comment 1195, RFC 1195. So these enables IS-IS to be applied to TCP/IP and OSI environments. Now, this type of IS-IS that was extended is normally referred to as integrated IS-IS. Now, IS-IS has been widely used in large ISP networks because of two things: its simplicity and high scalability. Please note, large ISP networks. Now, as you're going to realize, actually OSPF is used in enterprise networks, but it's rarely used in ISP networks. In ISP networks, they mostly use IS-IS. So in this particular chapter, you're supposed to understand why. What are the advantages of IS-IS over OSPF? So by the end of this chapter, you should be able to, number one, a volunteer.
Master IS-IS principles and configurations.
Yes.
And the second one is be familiar with differences between IS and OSPF.
And OSPF, very well. Let's begin with IS-IS principles. Now, generally, OSPF is normally used within an enterprise. Mostly, an enterprise network is also referred to as a campus network. A campus network has certain characteristics that you must understand. One of them is that it has a lower number of routers. And number two, it also covers a smaller area. Compared to what we call the ISP network, also known as the backbone network. So while this network here is just covering, for example, MMU, an ISP network like Safaricom's networks maybe covers the entire country. So in terms of coverage area, again, it covers a smaller area. Now, the other thing with campus networks is that they use what we call routing policies or policy-based routing. And most of the time, these policies that govern how the internet is accessed or the network resources is accessed within an organization or an enterprise, most of the time they change frequently in order to cater for new demands and policies within your organization. But in the backbone network or the ISP networks, most of the time we really do not change policies very frequently. So that's the other thing. So generally, OSPF is best suited for enterprise or campus networks. And as we saw, it normally divides routers into a variety of areas. As I've said, most of the time we have policies that can change frequently. Later on, we are going to learn about routing policies and also policy-based routing. Okay, so those are some of the characteristics of OSPF. When it comes to IS-IS, unlike the campus network, which normally has a hierarchical design architecture, where we have the access layer, the aggregation layer, and the core layer. When it comes to the ISP network, most of the time we have what we call a flat area rather than a hierarchical design. So this also just shows you the difference. Now, the other requirement on an ISP network, because it supports a greater number of users who need to access the internet all the time, an ISP network requires fast convergence. Fast convergence because it supports high transmission volumes. An ISP network is also supposed to be efficient, reliable, meaning it can recover very fast from failures. It's also supposed to have scalability, meaning it can expand to cater for demand. For example, new customer connections, and so on and so forth. So for those reasons, most of the time, ISPs use IS-IS. IS-IS is an IGP, just like OSPF, and therefore it is used, normally it's used within an autonomous system. But now, in order for the ISP to connect to other ISPs, of course, they'll have to use IS-IS also and BGP on their autonomous system boundary routers in order to connect to other ISPs. So IS-IS has many advantages in the ISPs networks, what we also call the backbone networks, including fast convergence. It also supports what we call PRC, or partial route calculation. It also involves what we call a simple packet structure known as TLV, type length value. I'm going to explain how that works in a little while. And it also enables faster neighbor relationship establishment compared to OSPF. And it also enables large capacity route transmission compared to OSPF. Therefore, it can support scalability. So let's see more about IS-IS. So intermediate system to intermediate system. Some characteristics. This is just the OSI layered model. What we have here is the TCP IP layered model. Now, going forward, we are going to be referring to integrated IS-IS just as IS-IS. But anytime we are talking of IS-IS, we are actually referring to integrated IS-IS. We said that after OSI, after the open, is it OSI? No, what do we call it? ISO, international. When ISO developed IS-IS for CLNP, IETF extended it in order for it to work on IP networks. And that is when the name was changed to integrated IS-IS. But we're not going to be saying integrated IS-IS, we're just going to refer to it as IS-IS. So it supports both connectionless networks and also IP networks, and it works at the data link layer, while the OSPF operates at the IP layer. So you're going to see, for example, when sharing IS-IS hello packets, we are going to be sending them using multicast MAC addresses and not multicast IP addresses. So IS-IS really operates at the data link layer using the MAC address rather than IP addresses. OSPF, on the other hand, only supports IP networks, and they cannot support CNLP, connectionless network protocol. So those are the basics of IS-IS. Okay, so let's move further and look at a few things here about IS-IS. So almost a similar process like OSPF. So the very first step is establishment of a neighbor relationship. Then you exchange networks you're aware of. So you synchronize your LSDBs and have the same thing. Then after that, everyone calculates their own SPF, performs SPF route calculation. And that involves creating the shortest path tree. So let's begin and look at, we look at the hello just slightly. So devices on two ends, two routers, are going to exchange hello packets initially in order to negotiate parameters. Parameters such as the network type, the circuit type. I'm going to tell you about the circuit type. We have level 1 routers, level 2 routers, level 1, 2 routers. The other parameters they exchange during neighbor establishment might include the area ID, the system ID, the IP address, and so on and so forth. So this process, again, is very similar to what we learned in OSPF. It is simply exchanging, and we're going to see it in detail in the coming slide. Exchanging parameters in order to establish a neighbor relationship. Then after that, we now start exchanging, in the next step here, we now start exchanging our link state information. Now, while OSPF was using link state advertisements to exchange link state information between neighbors, here IS-IS uses what we call link state protocol data units, link state PDUs. So going forward, we will be talking of LSPs. So that is why you can see here, we have LSP1, LSP2, and so on and so forth. Here we have LSP3, LSP4, and so on and so forth. Now, in order to exchange these LSPs, IS-IS uses two types of packets, what we call CSNP and PSNP. So I'm going to tell you about CSNP and PSNP in a short while. But they're the ones that are used to exchange and carry link state informations and the LSPs. Okay, now after that, it is the next thing is the route calculation. The route calculation is very similar to what happens in OSPF, except that in IS-IS, the algorithm separates the topology and the network, and therefore speeds up the network convergence. So as we are going to see when we describe this in detail, the creation of the shortest path tree is a little bit faster compared to how it's done in OSPF. Okay, so now let's look at how can I call this? So the title here is address structure. Now we have a table here. Now this table really is just comparing these two protocols, IS-IS and OSPF. So in the first column here, they are saying that OSPF was defined under the TCP/IP protocol stack, while IS-IS was defined under the OSI, the Open System Interconnection Model stack. So OSPF is an IP protocol, while this one was designed to be a CLNP, Connectionless Network Protocol. This one uses an IP address to exchange routes, while this one uses an address called the NSAP, address. Then to identify routers and areas, this one uses the area ID plus the router ID, which you already understand, while IS-IS uses the net identifier, So I'm not going to go into details about the NSAP. So the NSAP is made up of several fields, which I want you to read on later. IDP, DSP, then the IDP is made up of AFI and IDI, which I'm not going to go in detail into. DSP is made up of the high order DSP, system ID, and cell. Now, to put it a little bit easier, generally, the first part here is the area ID. Then the second part here is the system ID. Now, the area ID is used to identify the area that particular router belongs to. Then system ID is used to uniquely identify that router. So you can think of a system ID as the router ID. So here really, in OSPF, area ID is just the same here, while router ID is what you're calling system ID here. Then lastly, we have what we call the cell, this one here, the cell, which is 1 byte in size. The cell is used to specify, what did they say about the cell? The cell is used to indicate the network layer information. The network layer information of I'm trying to remember the cell. It's always 00. It's always 00. And it is used to, I'm forgetting, please check. I'm giving you that as a reading assignment. So the cell here is 00. This is what we call the cell, that part. So it's used to identify something like the type of service, something like that. And normally it's 00. Then the system ID is that one there. The area ID is this one here. So when configuring an IS-IS router, we are going to be configuring it with an area ID and also the system ID and the cell maybe. So this particular address, the NSAP address, is simply used to identify a router within an OSPF domain. Okay. So OSPF defines 3 router types. We are going to learn much more about each one of them. So the very first router is known as the level 1 router. Then another router is known as level 2 router. Then we have another router known as the level 1-2 router. So you must understand each one of them. What is a level 1 router? What is a level 2 router? What is a level 1-2 router? Now, generally, routers within the same area can establish neighbor relationships with other routers. And most of the time, a level 1 router can create a neighbor relationship with a level 1 router and a level 1-2 router. Then we can have another area. So to establish a level 1 adjacency, ensure that 2 routers use the same area ID. Okay, so if you're on the same area, then you're going to form level 1 neighbor relationship. But if you are on different areas, for example, this is area 1 and this is area 2, so you cannot be able to establish level 1 neighbor relationships. Now, level 1 routers will also have a link state database for that particular area, so it's known as the level 1 LSDB. On the other hand, you can have another area which you're going to talk about, known as the backbone area, where we put level 2 routers. Our level 2 routers can only have level 2 LSDBs. Now, the interconnection between level 1 and level 2 routers is what we call level 1-2 routers. And level 1-2 routers will have both the level 1 and the level 2 LSDBs. It is important to mention that when you configure a router with IS-IS, it will by default take the level 1-2 router type, unless now you change the IS level to either level 1 or level 2. Okay, so I'm going to mention most of the things as we go on about each of the routers. Okay, so for neighbor establishment, just like in OSPF, as I said earlier, we have the hello packet that is used to do that. The hello packet, just like in OSPF, is used to discover the neighbors, exchange parameters like the IP address, the circuit type. So the circuit type is what we were talking about, level 1, level 2. So which type of router are you? So that's what we call the circuit type. It's one of the parameters they exchange so that they can know whether they can form the neighbor relationship. Of course, it's also used to maintain neighbor relationship, neighbor relationship, and it's also used to it's also used as a keep alive packet to detect whether the neighbor is still up or the neighbor has gone down. So those are some of the functions of the hello packets. Okay, now in IS-IS, we call the hello packets, we call it the IS-IS hello packet. And therefore, most of the time, we also refer to it as IIH. Now, OSPF supports 4 different network types, but IS-IS only supports 2 network types, the point-to-point network type and the broadcast network type. So IS-IS does not support NBMA or point-to-multipoint, only 2 network types. Now, with that in mind, OSPF defines 3 different types of hello packets for different scenarios. One of them is known as the point-to-point IIH, IS-IS hello packet. The other one is known as level 1, LAN, IIH. Then the next one is known as level 2, LAN, IIH. So those are the 3 types of IIH packets that are supported. In IS-IS networks. Now, point-to-point IIH can only be used in point-to-point networks. Then level 1 LAN IHIH can only be supported in a broadcast network in a level 1 area, while level 2 LAN IHIH can only be supported in a broadcast level 2 area. Now, for example, if this area is a level 1 area, then this particular router, if it wants to establish neighbor relationships, it will send a level 1 LAN IHIH with the destination, with the multicast destination address. So this is the destination MAC address of that particular hello packet, L1, level 1 LAN IIH packet. So if this guy receives it, it will know, oh, I can process this, I can process this, I can process this. So what I'm saying at this particular point is that we use a multicast MAC address as the destination address when we want to send a hello packet within a broadcast network. Similarly, on a level 2 area, this is the reserved multicast MAC address. So this one ends with 0014, this one ends with 0015. So unlike OSPF packets which use multicast IP addresses, IS-IS is a data link layer protocol, and therefore the packets are exchanged using multicast MAC addresses. So I hope that is clear. Any question to this far? Anyone with a question or a comment? Okay, so I just wanted to ask, in a point-to-point network, because really, as we're going to see, in IS-IS, just like in OSPF, we have elections. So this is a broadcast network. We've said IS-IS supports broadcast, and it also supports point-to-point network type. So I want to ask, do you think we need to do an election in a P2P network? Anyone? Do you think we need to do an election in a point-to-point network? Yes or no?
Oh. No.
Yes?
I'm just guessing no, but not sure.
Okay. For you to be sure, you need to ask yourself, why do we do elections? When it comes to these protocols, why do we do elections in the first place? And when we were learning about OSPF, I explained a bit about this. Why do we do elections? Okay, so we really do elections in order to reduce the number of exchanges, the adjacency. So generally, in a point-to-point network, because we just have two routers, because in a point-to-point network, we have two routers interconnected together, most of the time via serial link, or just two routers even with an Ethernet cable. So when we have a point-to-point network type, we don't need to elect a designated router, for example, in OSPF. But in a broadcast network, so that everyone cannot talk with everyone else, but they can talk with, let me say, a central person or a leader, we need to do elections in order to reduce the exchanges and therefore improve the efficiency of sharing the LSAs. Okay. So let's look at the neighbor relationship establishment. We have two ways. We have two ways in which neighbor relationships can be created in IS-IS. One of them is called the two-way handshake, and the other one is called the three-way handshake. Now, in an IS-IS domain, every router will be defined by a unique system ID. So I think we just looked at this in a previous slide. So for example, so the system ID is like the router ID when it comes to OSPF. Now, in a point-to-point network, you can use two-way handshake, but in a broadcast network, you must use the three-way handshake. What is the difference between the two? In a point-to-point network, or when you're using two-way handshake, router A will send a point-to-point IIH to RTB. When RTB receives that IIH, the status will change immediately from down to up. Almost at the same time, RTB will also maybe send the IIH, and therefore the status of RTA will change to up. So it's only after your status has changed to up between the two that you can start exchanging the hello packets and the parameters now, the parameters. And the risk with a two-way handshake is that sometimes maybe you can just achieve unidirectional communication. Because if for example, after RTB, if after RTB receives this IIH, point-to-point IIH, if it sends parameters without, for example, sending the initial IIH, then this guy status might still be down. So that is what we call unidirectional communication. This status is down, and therefore, if you try to send, this guy cannot really reply to you. Okay, but when it comes to a three-way handshake, you'll actually confirm that you've achieved bidirectional communication. So how? So firstly, you'll send a LAN, either level 1 or level 2 LAN IIH with your system ID on that hello packet. Now, initially, your neighbor list will be empty. So when RTB receives it, when RTB receives this particular initial hello packet, its state is going to change from down to initialized. Now, almost at the same time, or after it receives it, it's gonna reply with its own LAN IIH with its own system ID, so 2, and on the neighbor list, it's going to indicate that RTA is my neighbor. Now, when RTA receives a hello packet and sees its system ID on the neighbor list of that hello packet, then it will now change its status from initialized to up. So RTA will also send to RTB another hello packet, and on its neighbor list, it's going to indicate RTB as its neighbor. And therefore, RTB state will also change now from transit from initialized to up. So it's only after they are, remember this is a broadcast network, it's only after they are on the up state that they can start what we call the DIS election. The DIS election. So in IS-IS, we call it designated intermediate system. So AKA DIS. So anytime we talk of DIS, we really are going to be referring to the intermediate system, DIS. So establishing neighbor relationship of the multi-access network type requires the three-way handshake. So you must use the three-way handshake. So those are the two ways. You can either do it using the two-way handshake or using the three-way handshake. Okay, so let's move on. So let's look at the comparison between the DR in an OSPF network and the DIS. So we can begin with the election priority here. Election priority. So in OSPF, we know that devices that have been configured with a priority of 0 cannot participate in elections. In IS-IS, devices with all priorities will participate in the election. Now, the router with the highest router ID in OSPF, with the highest priority, will be elected as the DR. Similarly, in DIS, the router with the highest priority will be elected as the DIS. The only difference comes with the second part. For example, a DR, if the router priorities are the same, then it will go down to the highest configured loopback address, then highest configured physical address. But for a DIS selection, it goes to the router with the highest MAC address. So if the router priorities are the same, then it goes to the router with the highest MAC address becomes or is elected as the DIS. Just like in OSPF, a router that becomes a DIS really creates a virtual router, what we call a pseudonode, which now acts as the central point of communication between all the routers in that particular network segment. So the functions of a DR in OSPF is very similar to the functions of a DIS in IS-IS. Okay, election waiting time. So this one will wait after the neighbor relationship has been established. They'll wait for 2 hello intervals. 2 hello intervals. By default, non-DIS routers send hello packets after every 10 seconds. So it will wait for roughly 20 seconds. Roughly 20 seconds before they begin the election. But in OSPF, they have to wait after forming the neighbor relationship, establishing the neighbor relationship, they have to wait for 40 seconds. Backup, we know that in OSPF we have a BDR and we know the purpose of the BDR, but in IS-IS we only have the DIS, we do not have a backup. Adjacency, we know that the DR and the BDR will form adjacency with all the other routers in an OSPF network. But DR others Dear others will not establish adjacencies. Their relationship will end at the neighbor relationship in a state we call the two-way state. But in IS-IS, all the routers will establish adjacencies. Now, preemption. Preemption is if a router is introduced in the network that has a better priority, is it going to trigger an election? In OSPF, no. We have already elected a DR. You cannot just come in with a better priority and now you want to become the DR. So it will not preempt the elected DR. In IS-IS, yes. So if you introduce a router here, if you introduce another router here, and it has a better priority, then really elections are going to be held again, and that guy is going to be elected. Function. So I told you that I said I'll tell you about CSNPs, and I'm still going to tell you about that in a short while. So it sends CSNPs periodically to guarantee LSDB synchronization on multi-access networks. Multi-access networks are simply broadcast networks, like this one here. It's a broadcast network. This one uses LSA flooding in order to ensure LSDB synchronization. So those are some of the points that you need to understand. Those are some of the points that you need to understand about DIS and DR. Okay, so now let's look at the link state information transmission. How is it done? How do we exchange link state information? How do we exchange link state information? Now, as we already said, OSPF uses link state advertisements, but IS-IS uses link state PDUs, link state protocol data unit. Is used to exchange link state information. Now we have real nodes, LSP. So real node means it's a real router. Pseudo node means it's a DIS. So it only exists in broadcast links because it's in broadcast links that will have an election. Now we have what we call CNP PDU. So CNP is what we call the sequence number PDU. And now we have two types. We have two types of this. The first one is called the complete sequence number PDU. The second one is called the partial sequence number PDU. Sorry. Now this is what I was telling you that I'm going to tell you about it. PSNP and CSNP. Now it is sequence number PDU that are used to maintain and synchronize the LSDB, and they carry the summary information. Now, generally, this guy here, CSNP, is used to carry the summary. So let me just write, it contains the summary of all link state BPDUs in an LSDB. So in the gonna the entire summary, every location you know about. So that is what we call a complete sequence number. On the other hand, this one here contains the summary of some LSPs. So not all, some in an LSDB, and can be used to request and also acknowledge LSPs. Now let me even simplify it further. Now a complete sequence number PDU is very similar to database description packets, DD packets, DD packets in OSPF. On the other hand, partial sequence number PDU is now used in a similar manner as the link state request and link state acknowledgement in OSPF. So initially, routers are going to send out a CSNP, giving a summary of all the locations they know about. So I know about Kitale, I know about Eldoret, I know how to go to Kisumu, I know how to go to Busia, and so on and so forth. So the complete list. Now, when a router receives that list, it will compare it with its own LSDB. If it finds that, hey, this guy knows how to go to Busia, but I don't know how to go to Busia, then it's gonna send out a PSNP. Hey, tell me how to go to Busia. So you see, that is very similar to the link state request in OSPF. So generally, that is what we call the sequence number PDU. So we have two: complete sequence number PDU and the partial sequence number PDU. Okay, what else am I supposed to talk about? LSPs. This link state, the link state PDUs, LSPs. We have level 1 LSPs, we have level 2 LSPs, and we have level 1, 2 LSPs. Each one of them is carried by the respective router and is transmitted by the respective router. So a level 1 router will transmit level 1 LSPs, and it can also transmit level 1, 2. Just level 1 LSPs. Level 2 router can only transmit level 2 LSPs. On the other hand, level 1, 2 router can now transmit both level 1 and level 2 LSPs. Now, other than mentioning that, the other important thing to mention about LSPs is, remember we've said that LSPs is a link state PDUs. So this is what we call LSPs. Now, LSPs have two important fields. Sorry. Number one, we have what we call the ATT field, and the second one is called the IS type field. Now, the ATT field is used to indicate indicates that an LSP has been transmitted by a level 1-2 router. So if this field is set, if you receive an LSP and the ATT field is set, you know that this LSP is actually coming from a level 1-2 router. Then the IS field is used to indicate whether the LSP has been generated either by a level 1 or a level 2 router. So if the LSP is coming from a level 1 router, then the IS type field is going to have a certain binary value. If it's having maybe 0, if it's coming from a level 2 router, then it's going to have a different value, maybe 1. I'm not very sure at this point. So that's the other thing that I needed to mention about link state PDUs. Okay. Oh, I also didn't talk about TLV. TLV is what we normally refer to as a type length value. So the IS-IS packet structure takes this modular structure. Most of the time when we say that a protocol takes the TLV structure, it means that that protocol can be extended. We can add different headers and different other capabilities to it by simply specifying the type and the length of that particular header, and now the data or the value of that particular header that we are adding to this particular packet. So that is important because it ensures that the protocol is flexible, and therefore adding other capabilities to the protocol becomes a little bit easy. So the protocol can grow when it adapts the TLV structure, type length value structure. So this ensures that also the protocol is scalable. It can be able to grow to accommodate many other features with time. Okay, so let's move on and look at link state information exchange. So how is the information sent between the routers? So we have a line here. So this side, we want to see how link state information is exchanged on point-to-point networks. Then here we are going to see how it's done in broadcast networks. So after establishing neighbor relationship and the status of the routers RTA and RTB are up, RTA, for example, is going to send a CSNP, so complete sequence number BPDU. So that is simply a list of all the routes it's aware about, but remember it's a summary. So you're not saying how to go to Kitale, how to go to Busia, no. You're simply saying, I know how to go to, I know how to go to. All the networks that RTA is aware of. Then RTB, once it receives this CSNP, it's gonna compare it with what it has. Then it's gonna send a partial sequence number, BPDU, to request to be given directions of networks that it is not aware of. So it's gonna send that. Now, after sending that, now this guy is going to reply with an LSP, link state BPDU, PDU, link state PDU, giving the information of the requested network. Now, after giving that information, this guy is supposed to respond with an acknowledgement. The acknowledgement is supposed to be sent using PSNP. Now, in case this acknowledgement does not arrive to RTA within a certain amount of time, RTA is going to send details about that network again. So it's going to retransmit it. So we have a time that it will wait, predefined time. It's called the retransmission time. So if it expires, you send the same details again. So after that, if this guy receives it, they're going to send an acknowledgement. So PSNP here is simply an acknowledgement. This PSNP here is simply sending a request. Hey, tell me how to go to Busia. Then this guy tells you, hey, this is how you go to Busia. Okay, I've gotten it, but this one does not arrive. So if this does not arrive, then these will send the directions to Busia again. This is how you go to Busia. Then you send, hey, okay, I've seen how to go to Busia. So that is how link state information is exchanged on a point-to-point network. So here they say SNPs are sent only once on a P2P network. That is, a CSNP is sent immediately after a neighbor relationship is established. So you see, you only send once because it's only two. We only have two routers. So you only send it once, a complete list of all the networks you're aware of. Okay, but what about on a broadcast network? So on a broadcast network, for example here, who is acting as the DIS? Is it RTB? Oh. Okay, I think who is RTA? RTB, this guy here. RTB is the DIS, designated intermediate system. So what happens is after forming the neighbor relationships with the DIS, then for example RTC will send an LSP, which is a fragment of the networks it knows about. So it will send it to the DIS. So that is step number one. When the DIS receives it, the DIS is going to send it everything it has. So a complete sequence number PDU. So the routes it has learned from router A, from router B, from router C. It's gonna flood it on the multi-access network. And when either RTA or RTC receives it, it's gonna request details of networks it's not aware about. So using a PSNP, hey, tell me about this network, tell me about this network, tell me about this network. Then the DIS is going to respond using an LSP, link state PDU. So I'm gonna tell you about how to go to network A, how to go to B, how to go to B. So CNPs are multicast only by the DIS on a multi-access network, and they're normally sent after every 10 seconds. So after every 10 seconds, a DIS will flood the CSNP in that multi-access network. So I hope that is clear. I hope that is clear. Okay, so any question about how link state information is exchanged on an IS-IS network? Any question or comment, ladies and gentlemen? Okay. So let's move on. So at this point, we want to understand yeah, okay. So I think I had skipped this slide. So as we said earlier, IS-IS uses the same algorithm. It uses the very same algorithm as OSPF in calculating routes. So it uses the SPF. It works in a similar manner. So after you've received the complete LSDB from either the DIS or from your neighbor in a point-to-point network, then you generate the network topology, then you create the shortest path tree using yourself as the root. So we did this process when we were doing OSPF. So for example, here they're just showing the example of RTA. So RTA will create its RPT or is it SPT, shortest path tree, with itself as the root. So it will create that, showing how to go to all the other networks. Now, the default interface cost in IS-IS is 10. The default interface cost is 10. And when it comes to IS-IS interface cost, we have two ways to do it. One of them is called the narrow mode, and the next one is called the wide mode. Now, I actually learned about this, but I've forgotten a little bit, and the notes on HCIP is not giving it, is not explaining it very well. So I'm giving you this as a reading assignment. In HCIE, they explain it a little bit deeper, but please go and learn the difference between the two. But in the moment, please know that for both modes, the default interface cost is 10. If you can remember, the default interface cost, I think for OSPF was 1 or something. So here it's 10. But you can still manually configure it in order to change it. Oh, no. I talked about the OSPF default cost being 1, but actually in OSPF, the cost is based on the bandwidth. Reference bandwidth is calculated based on the reference bandwidth. Now, there is a command that you can use on an interface. That command is called autocost enable. If you use this command on an interface, then the interface cost will be calculated based on the interface bandwidth instead of using the default cost. So if you want cost in IS-IS to be calculated based on the bandwidth, you use the command autocost enable. Okay. Let's move on to the next one. Network hierarchy and routing domain. We already said that we have 3 types of routers in an IS-IS routing domain: level 1 routers, level 2 routers, and level 1-2 routers. Now, unlike in OSPF, the IS-IS boundary is a router rather than an interface. In OSPF, it is the interface that belongs to an area and not a router. Now, IS-IS also has areas. Like here we have area 2, area 4, area 5, area 3, and we have area 1. Now, what we are saying is that this router here, the entire router belongs to area 2 and also belongs to area 1. So it is not the interface. It's not this interface belonging to area 1, then this interface belongs to area 2. No, it is per router, not per interface based. So the router can belong to 2 areas. Now, how the areas are determined is like this. We have 2 hierarchies of areas. One of them is called the boundary. This is the backbone. The backbone area. So let me just indicate that. So this area here is called the backbone area. The backbone area, and all the other areas are called non-backbone areas. So non-backbone areas like area 4, area 5, area 3, area 2 can only communicate with each other through the backbone area. So the backbone area is the transit area between the other areas. Now, in the non-backbone areas, that is where the level 1 routers reside. So any router that belongs to a single, it belongs to a single non-backbone area. If it belongs to a single non-backbone area, and then that is a level 1 router. On the other hand, within the backbone area, like area 1 here, all the internal routers within the backbone area are normally configured as level 2 routers. Now, any router that belongs to a backbone area and a non-backbone area is normally what we refer to as the level 1-2, level 1-2, level 1-2 router. So each of these router has certain characteristics. So let's look at the level 1 router. Now the level 1 router will only have LSPs of routers in the local area. So inside the routing table of this particular router, you're only going to have routes of other level 1 routers that are within this area. So the routing table of a level 1 router cannot contain routes from other areas, only from within the area. But in order to be able to communicate with other areas, then it will normally contain a default route whose next hop is the level 1-2 router. So it will have a default route whose next hop, the next hop is the level 1-2 router. So you can almost think of this as a totally stub area in OSPF. It also looks like this, because a totally stub area, you cannot import type 3. You cannot import networks from other areas into a totally stub area. So I want to compare level 1 routers with a router that is in a totally stub area in OSPF. Okay, and let's go to level 1-2. Level 1-2 routers. Now, level 1-2 routers normally will belong to a backbone area, and maybe also to an unbackbone area. So you see, for example, this router here, we've configured it as a level 1-2 due to future expansion, but it does not, okay, maybe it belongs to area 1 and area 2, but it's not connecting to any other router. So normally, a level 1-2 router will belong to the backbone and another non-backbone area. The other thing is that it will have 2 LSDBs. It will have 2 LSDBs, a link state database for area 1, and it will also have a link state database for area 4. So generally, a level 1-2 router, in its routing table, it will contain the routing information of the entire network. The routing information of the entire network. Now, anytime a level 1-2 router generates an LSP into a level 1 router, it will set the ATT bit to 1. You remember I mentioned the ATT field in the previous slide. So anytime it's sharing an LSP within a level 1 area, then it's going to set the ATT bit to 1. So that is important. Then, of course, the last one now is a level 2 router. So level 2 router has only a level 2 LSDB. So its LSDB has routers in the backbone area, but it has no LSPs from the non-backbone areas. So level 2 iko tu na hiyo. However, level 2 routers also in their routing table, they contain information regarding the entire network, because to get to any of these other networks, it only needs to get to the level 1, 2 routers. So those are some of the characteristics of each of those routers. Okay, so let's look at, did I skip something? Okay, so let's look at inter-area routing. Inter-area routing. So for example, here we have area 1 and we have area 2. So area 2 here is our backbone area. So in our backbone area, we have level 2 routers. So level 2 routers, as I explained earlier, can form neighbor relationships with other level 2 routers, and they can also form neighbor relationships with level 1, 2 routers. Now, in an backbone area, level 1 routers can establish a relationship with a neighbor relationship with a level 1, 2 router, and it can also establish relationships with other level 1 routers. So that is how then, so what are they saying here? So in area 1, if area 1 wants to access area 2, the level 1, 2 router, RTA, generates an LSP with the ATT bit set to 1. So this guy wants to enable these guys to access these guys. So it will generate a level 1, 2 route with the ATT bit set to 1. Then a level 1 router will generate a default route with the next hop pointing to the level 1 router after receiving the LSP with the ATT bit set to 1. So anyone inside here, like this guy, will simply use this as the next hop in order to get to these guys. And it's almost similar for this side. So if routers, level 2 routers here in area 2 want to access routers in area 1, then the level 1, 2 router will add specific routes to area to this particular area in the level 2 LSDB. Then the level 2 router will calculate specific routes to area 1 through SPF calculation. So that is how that is done. Now let's look at some of the differences between IS-IS and OSPF. So the first notable difference is the network types. So while OSPF has 4 network types, IS-IS only has 2 network types. The other one is cost style. We've seen that we have narrow and we also have wide compatible costing in IS-IS. But in OSPF, we simply use the bandwidth, which is simpler compared to the IS-IS models of calculating the cost. Then also the area types. So in OSPF, we have so many area types. We have the backbone, non-backbone. We have special areas like the stub, totally stub, NSSA, totally NSSA. But in IS-IS, we have only two area types, backbone and non-backbone, period. Then the packet types in IS-IS, they're quite simple. We only have CSNP, LSP, and PPP, the partial sequence number, PDU. So quite simple. But in OSPF, there are so many. We saw type 1, type 2, type 3, type 4, type 5, and type 7. And there are even more. If you do HCIP, you're going to learn the others, HCIE. Then you have route convergence. So even though OSPF has a fast route convergence mechanism compared, for example, to RIP and other predecessor routing protocols, IS-IS is faster because it implements methods such as partial route calculation and incremental SPF. Then the other thing is on scalability. The main reason as to why IS-IS is normally used in ISP's networks is because of scalability, one of them, other than convergence speeds, faster convergence speeds. The other one is scalability. So the scalability here is higher because it uses a flat architecture compared to OSPF that uses very many areas and therefore can become quite complicated with time. Then the routing load capacity. So this one is high, but this one has more routes in each router. So you need more powerful routers in terms of their processing power and also storage space. So those are some of the issues that you should understand about those two protocols. So this is just a list of some of the terms that we've come across so far and how they are referred to by these different teams. So that is how they refer to them. So an IS, intermediate system, is simply a router. ES, end system, IETF, they call it host, something like that. Then designated intermediate system or designated router in OSPF. System ID or router ID in OSPF. Link state PDU or link state advertisement in OSPF. IIH, IS-IS hello PDU or simply hello packet in OSPF. PSNP, partial sequence number PDU, is very similar to LSR and LSAC in OSPF. Then we have the complete sequence number PDU, which is very similar to the function of the database description packet in OSPF. So how do we configure? Can someone help us read these particular requirements? A volunteer, please, as we wind up.
In the figure, all routers in the customer network need to run intermediate system to intermediate system to ensure reachable routes on the network.
On the network,
all
yes.
IS-IS processes, yes, all IS-IS processes use the process ID 100. Router A is the DIS in area 49, area 1.
Just a moment, so that we mark a few things. Okay. So, number one, we want to use IS-IS in the entire network. Number two, the IS-IS process ID should be 100. Go on. From RTA.
Router A is the DIS in area 1.
Okay.
Yeah.
Go ahead.
the network between router D and router E must be point-to-point network.
So we want to configure this network here to be a point-to-point. Why do you think that is important? Someone else can answer that. From the topology, why do you think we should configure this as a point-to-point? Yet we've connected it using an Ethernet cable. So when we configure the network type to be point-to-point, what are we trying to avoid?
Election.
Exactly, election. Okay, move on. RTE.
Router E imports the direct route 192.168.x.x and requires router A to access area 2 through the optimal path.
Okay, so we want RTA to access area 2 through the optimal path. So I'm also going to show you what that means, through the optimal path. Okay, move on.
Perform the configuration correctly to meet the preceding customer requirements.
Okay, so generally, number one, we need to configure IS-IS to run on all the routers with a process of ID of 100. Number two, we configure RTA to be the DIS. What do we need to change in RTA to make it the DIS in this? You see here, we are going to have an election because that is a broadcast network, right? So what do we need to configure in RTA in order to ensure that it becomes the DIS in that area? Someone? The router priority, right?
Yes.
Tumesema elections inafanywa based on the router priority. Okay, then RTD and RTE must be PPP. We've already said that the reason for that is so that we don't have elections here, because after all, we only have 2 routers. Then RT imports the direct route. So we're going to import. So in IS-IS, you can also import external routes into IS-IS. Then RTA to access area 2 through the optimal path. So you see, RTA has 2 options. It can access area 2 using this level 1-2 router RTB or using RTC. So which way do you think is more efficient between the two? Accessing through RTB or RTC?
RTB.
RTB. Reason?
RTC is connected to RTB using a serial connection.
Yeah, which has a lower speed, 2 Mbps, while the Ethernet cable has a speed of 100 Mbps. So RTB is clearly the optimal path. So we want to ensure that even though it has 2 options, because we have 2 level 1, we have 2 level 1-2 routers. So we just want to ensure that it's going to use RTB rather than using RTC to access this part. Okay, so let's try and see how that can be done. So how do we configure IS-IS? You configure IS-IS, let's begin with RTA by going into system view, then you type the IS-IS command and the process ID. So we've been told the process ID should be 100. Then after that, you're going to go into the IS-IS 100 view, then you use the command called network entity. Network entity, then you type the net. Simply the net will include the area ID. So 49.0.0.0, so that's the area that it belongs to. Then the next part is used to define the system ID there. Then the last part should always be 0, 2 zeros. So the system ID for RTA is 1. Then after that, we say that by default, IS-IS routers are level 1, 2 routers, but we want to configure this one as a level 1 router. So to do that, we use the command is-level, then we select level 1. Now, after doing that, the next thing you need to do is to go to this interface in RTA and enable IS-IS. So you use the command IS-IS enable 100. The other thing we're going to do there is to change the IS-IS priority so that RTA can be elected as the DIS. So the command is IS-IS DIS priority 120. Then we are changing the priority for this particular area, which is level 1. So we specify that. So for RTB, we've simply done the same thing, only that now we are not changing the priority for RTB. Similarly, for RTC, we've also done the same thing. And the only thing we are changing is the system ID, the system ID. So that is what we've done here. So we can move on to the next one and see what has been done to meet the other requirements. Okay, so for RTD and RTE, they are, oh, okay, sorry. Here, I need to mention that as you can observe, these RTB and RTC are level 1, 2 routers. So because by default, when you configure IS-IS, the router becomes a level 1, 2 router. So we don't need to use this command to change the level. So that's why we don't have that command there here on RTB and RTC. Okay. So IS-IS route configuration part 2. So now we configure RTD and RTE. They are supposed to be level 2 routers and in area 2. So let's see whether that has been met. So the IS-IS process indeed is 100. Then we use the network entity to specify the area. So indeed, the area is area 2. Then the ID for router 4, RTD, is that one. And that one will always remain 00. So here again, we have to change the level using the IS level command. Then we go to the interface and enable IS-IS 100. And remember we said we don't want an election between RTD and RTE, even though they are connected over an Ethernet cable. So to avoid that, on that interface, you specify the circuit type as point-to-point. You specify the circuit type as point-to-point. So IS-IS circuit-type P2P. Okay, so let's move on to the next one and see what we have. So here, we are doing two of the requirements. Number one, RTE wants to import these direct routes into IS-IS. So the command to do that, you go into IS-IS 100, then you use the command import route direct, just like in OSPF. So it's going to import these routes in this particular area and share it with RTD. Okay, then the other thing we said is we want to ensure that when RTA is accessing area 2, it accesses it through RTB and not through RTC. And not through RTC. So how can that be achieved? Okay. So let me just explain something here. Now, remember, in a level 1 area, we do not import, we do not advertise networks from other areas. So if RTA wants to access, routers on another area, it has to go through the border router here, the level 1-2 router. But now there are two. Now the only cost that RTA can calculate, because it has a default route, to this guy and to this guy, that if you want to go to other areas, you can either go through this guy and through this guy. So the only cost RTA is aware of is the internal cost from itself to this border and to that border, which, for example, in this case, it's the same. They have the same cost, both RTB and RTC. But if we want RTA to be aware of the cost from itself, for example, to RTD, now we need to import. We need to do an import. So you see, if we go to RTB, then we have to go to area 1. Then we use the import command. So import route IS-IS level 2 into level 1. So what we are simply doing is importing the level 2 routes into this area. By doing that, RTA can calculate the total cost from RTA to RTD, and therefore it can know that when I use RTB, then the cost is better than when I use RTC, and therefore it's not going to use this suboptimal path. So you have to do the same also on RTC. So you import the level 2 IS-IS level 2 into level 1. So that is how you ensure that routers in an unbackbone area can use optimal paths in case you have two boundary routers. So we're just calling them boundary routers for lack of a better word. Okay. So ladies and gentlemen, that is it about IS-IS. I hope you've learned something and you've enjoyed the lesson. I now want to invite you to ask a question or clarification that you might need, and to also help me answer these questions. Okay, so let's go ahead. Anyone with a question? Okay, so the first question, how many IS-IS router types exist? A volunteer?
3.
Very true. Which one, and which one?
Level 1, level 2, and level 1.
Okay, very well. Thank you. What is the function of the partial sequence number PDUs in neighbor interaction? What is the function?
Sends updates.
Used to request, to request and acknowledge LSPs, link state PDUs. Thank you very much. What are the advantages of IS-IS compared to OSPF? Let me leave that with you so you can have a read about that. So thank you very much, guys, for the privilege of your time. We can now go and do the lab for IS-IS. Asanteni sana.